What is the main problem addressed in the paper regarding the use of large language models, LLMs, in workflow generation?
The main problem addressed in the paper regarding the use of large language models, LLMs, in workflow generation is the issue of hallucination. Hallucination refers to the generation of properties, such as steps or tables in the workflow, that do not actually exist. This is a significant concern when using LLMs for structured output tasks like converting natural language to workflows, as generating inaccurate or non-existent components can lead to unreliable and untrustworthy outputs. The paper highlights that using LLMs naively can result in hallucinations, which can be particularly problematic when the natural language input is out of distribution or when enterprise users need to customize their workflows. To mitigate this issue, the paper introduces Retrieval-Augmented Generation, RAG, as a method to reduce hallucination and improve the trustworthiness of the generated workflows. By incorporating a retriever to provide relevant information before generating text, the RAG approach aims to ensure that the output workflows contain valid and executable components, thereby addressing the problem of hallucination associated with LLMs in workflow generation.
How does the proposed Retrieval-Augmented Generation, RAG method work in the context of generating workflows from natural language requirements? Illustrate step by step.
The proposed Retrieval-Augmented Generation, RAG, method works in the context of generating workflows from natural language requirements by first training a retriever encoder to align natural language with JSON objects. This retriever is fine-tuned to map natural language to existing step and database table names, reducing the risk of hallucination in the generated workflows. The retriever is trained on pairs of user queries and corresponding steps or tables, using contrastive loss to minimize the distance between positive and negative pairs. During initialization, an index of steps and tables is built using FAISS, and when a user submits a request, the retriever suggests steps and tables based on the natural language query. These suggestions are then appended to the user query to form the input prompt for the large language model, LLM. The LLM is trained separately in a RAG fashion, where the retriever's output is included in the LLM prompt. By inserting the retriever's output in JSON format into the LLM input, the structured output task becomes easier for the LLM as it can copy the relevant JSON objects during generation. The LLM generates the workflow in JSON format via greedy decoding, ensuring that the output JSON properties exist and can be executed. The suggested tables and steps from the retriever are included in the LLM prompt, except for the most frequent steps, assuming the retriever has 100% recall. This approach aims to reduce hallucination while improving the overall performance of the system by providing the LLM with relevant information retrieved by the retriever.
What are the specific theoretical or practical benefits of using the Retrieval-Augmented Generation, RAG method in the workflow generation application described in the paper?
The specific theoretical and practical benefits of using the Retrieval-Augmented Generation, RAG method in the workflow generation application described in the paper include 1. Reducing hallucination. RAG helps in decreasing the generation of false or non-existent information, such as steps or tables, in the output JSON documents. This is crucial in ensuring the trustworthiness of the generated workflows, by minimizing the chances of producing inaccurate or irrelevant steps or tables. 2. Improving output quality. By incorporating RAG, the system can enhance the quality of the generated workflows. The method allows for the retrieval of relevant information from specific data sources before generating text, which in turn aids in producing more accurate and contextually appropriate JSON objects. 3. Enhancing trustworthiness. RAG contributes to improving the trustworthiness of the output by providing plausible JSON objects to the large language models, LLMs, before generation. This process increases the likelihood that the generated JSON properties exist and can be executed, thereby enhancing the overall reliability of the workflows. 4. Enabling customization. RAG facilitates the customization of workflows by allowing users to specify their requirements in natural language. This feature is particularly beneficial for enterprise users who need to tailor their applications, as RAG helps in minimizing the out-of-distribution mismatch and adapting to diverse user needs. 5. Optimizing model deployment. RAG enables the deployment of smaller LLMs while maintaining performance quality. This is advantageous in terms of reducing infrastructure costs and optimizing the system's footprint, making it more efficient and cost-effective for commercial applications. 6. Increasing system accessibility. RAG makes structured output tasks more accessible by providing a method to generate valid structured outputs from natural language inputs. This accessibility is crucial for users who may not have specialized knowledge in building workflows, thereby lowering the barrier to entry for utilizing such systems. 7. Enhancing retrieval training. RAG involves training a retriever model to align natural language with JSON objects, improving the mapping between text and structured data. This training process enhances the retriever's ability to retrieve relevant information and contribute to the overall effectiveness of the workflow generation system. 8. Supporting in-context learning. RAG assists in scenarios where in-context learning is impractical due to a potentially large and customizable pool of workflow steps. By providing relevant JSON objects to the LLM before generation, RAG supports the generation of valid and executable workflows even in complex and customizable deployment settings. 9. Facilitating structured output generation. RAG aids in generating valid structured outputs from natural language queries, ensuring that the resulting workflows can be parsed, interpreted, and executed correctly. This capability is essential for tasks like text-to-code or text-to-SQL conversions, where accuracy and reliability are paramount. 10. Enhancing system performance. RAG fine-tuning contributes to improving the overall performance of the system by reducing hallucination, increasing output quality, and enabling the deployment of smaller LLMs without compromising performance. This enhancement leads to more efficient and effective workflow generation in commercial applications.
How are the retriever and LLM trained in the proposed methodology?
In the proposed methodology, the retriever is trained by fine-tuning a retriever model using pairs of user queries and corresponding steps or tables. The retriever is trained to map natural language to existing step and database table names to reduce hallucination in the output. The retriever encoder is trained to align natural language with JSON objects by encoding both the user query and the step or table JSON object into fixed-length vectors using a Siamese transformer encoder with mean pooling. The retriever model is trained using a contrastive loss to minimize the distance between positive pairs, y equals 1, and negative pairs, y equals 0. On the other hand, the LLM is trained separately from the retriever. The LLM is trained in a Retrieval-Augmented Generation (RAG) fashion by including the retriever's output in its prompt. The trained retriever is used to augment the dataset with suggested step and table names for each example, which are then used in the LLM training. By inserting the retriever's output in JSON format into the LLM input, the structured output task becomes easier for the LLM as it can copy the relevant JSON objects during generation. The LLM is trained using standard supervised fine-tuning, with the retriever's output aiding in generating valid JSON documents while reducing hallucination in the output.
What are the key metrics used to evaluate the performance of the Retrieval-Augmented Generation (RAG) system in the experiments conducted by the authors?
The key metrics used to evaluate the performance of the Retrieval-Augmented Generation (RAG) system in the experiments conducted by the authors are trigger exact match, M, bag of steps, BOFS, hallucinated tables, HT, and hallucinated steps, HS. Trigger exact match verifies if the generated JSON trigger exactly matches the ground truth, including the table name if required. Bag of steps measures the overlap between the generated JSON steps and the ground truth steps in an order-agnostic manner. Hallucinated tables and hallucinated steps metrics measure the percentage of generated tables, steps that do not exist per workflow, indicating hallucination by the LLM. Lower values are better for hallucinated tables and hallucinated steps metrics. Additionally, recall at 1.5 is used to evaluate the retriever for steps, and recall at 10 for tables, ensuring that the top K retrieved steps tables cover the set of steps and tables in the JSON document representing the workflow.
Based on the results and analysis provided, what are the main insights regarding the impact of model size and fine-tuning on the performance of the proposed RAG system?
Based on the results and analysis provided in the paper, the main insights regarding the impact of model size and fine-tuning on the performance of the proposed Retrieval-Augmented Generation (RAG) system are as follows. 1. Model size impact. Scaling the size of the off-the-shelf encoders, such as GTR-T5, did not yield significant improvements on retrieval metrics. However, fine-tuning the encoder, especially the smallest encoders, 110M parameters, significantly improved performance. Larger LLMs can better copy and paste retrieved steps and tables during generation, leading to improvements in bag of steps and trigger exact match metrics. 2. Fine-tuning impact. Fine-tuning the RAG models with the retriever's output in JSON format significantly reduced hallucination in the generated workflows. Without a retriever, the percentage of hallucinated steps and tables was high, but with the retriever, these percentages decreased notably. Fine-tuning the RAG models allowed for valid JSON document generation following the expected schema, improving overall performance. 3. Optimal model size. The 7B version of the RAG fine-tuned model provided the best trade-off between performance and model size. The 3B version also showed competitive results, even compared to the larger 15. 5B version, highlighting the potential for deploying a smaller model if infrastructure constraints exist. 4. Comparison with other models. When comparing the RAG fine-tuned StarCoder-based 7B model to more recent LLMs of the same size, such as CodeLlama 7B and Mistral 7B VO. 1. The StarCoder-based 7B model outperformed them across all metrics. Pre-training on large amounts of natural language data may have been detrimental to the task, emphasizing the importance of fine-tuning for specific applications. In conclusion, the insights suggest that the optimal performance of the RAG system is achieved through fine-tuning smaller LLMs with the retriever's output, rather than relying solely on off-the-shelf larger models. Fine-tuning improves the system's ability to generate accurate and non-hallucinated workflows, demonstrating the effectiveness of the proposed approach in structured output tasks.